And we are recording. Oh, this thing not. Oh, no. Well, all right. Battery really good on this? All right, and we have sound. Oh, yeah. So it is Lab Day Wednesday. All right. So we're looking at here. Here's the 4 things we're doing today. All right, so I've got the starter question. We'll look at these guys in a moment. Look at the other main things on our agenda. So I'm going to fit in 3 labs today. This could be a bit different than we normally do this. So one of these labs is going to be just a classic collisions lab. I'm going to have cars on a low friction track slammed against each other. We'll look at what it would mean to have an elastic versus inelastic collision. Now, this one, I'm not going to have you guys write anything down, but I do want to take you guys through the thought process, because this one's kind of tricky to do it exactly. But I'll walk you through the thought process, like, how would you do this lab? Okay? And if you're at home, you may have printed out a couple of tables that look kind of like these. Okay, so I'll be stepping along with those. Yeah, I'm not going to have you guys write anything for that one, more of a demo, kind of like an extended demo. Okay. We will do both of these. I'll have you guys record data. We'll have some bouncy balls. All these are going to be bouncing off the ground. And we'll do something with, I'm going to unscrew this ballpoint pen, and we'll make use of the spring in this cartridge and bring this around and do elaborate related to that. Okay. All right, then, something else to have. Now, if you're in class, I will pass out this pretty soon. This is just a structured lab. So we've got some questions you're going to ask. Now, one of the differences of the labs today is that, okay, we're thinking ahead a little bit, but these 2 labs, the bouncy balls and the ink cartridge and the spring, I will let you guys choose which one you want to do a write-up for. I'll have you guys record all the data, okay? But I'll just figure out which one you want to do a write-up for, where you've got a question, what measuring tools would be involved, okay? What data would you have to gather. Of course, we'll gather all the data together for the class. Okay? And then here's where everybody's page is probably going to start to look pretty different. How are you going to use that data to answer this question? Might be an equation, might be a property of a graph, something like that. And then conclusion, what is the answer to your question? But I'll let you guys figure out what question you want to ask. Okay, so there could be like several questions you could ask about, especially the bouncy balls. I can think of quite a few questions. Okay. All right, so also you guys want to keep in mind, AP Classroom, we're going to go over the most missed multiple choice questions tomorrow, so have those turned in tonight. College physics, I had you guys do a handful of problems, so I'll pick those up on Friday. Okay? And then I did also assign you guys 2 AP videos, so this weekend I'll go and just see who's watched them, and if you watch them, I'll give you guys some points. So if you guys know that, just a reminder. All right, here's guys' starter question. So we've got Alan and Chad. Right, here's Alan and Chad. They're standing on frictionless ice. Ooh, frictionless surface. That's a lot like that magic school bus field, isn't it? It's frictionless surface. Alan throws a ball to Chad, and let's say you know the speed. They throws it. Notice this is relative to the ground. No, you'd probably assume that anyway, but here's a side thought. How many guys have been working on that girl walking on the plank problem? Right? And I did tell you guys yesterday that one takes some thinking for sure, right? There was, you guys remember there was like a girl walking on a plank on the ice, and one of the things that makes that problem kind of involved is that you've got the speed, you've got 3 different velocities you're dealing with, right? You've got the velocity of the girl relative to the plank, the velocity of the plank relative to the ice, and the velocity of the girl relative to the ice. There's like 3 different velocities you got to juggle. Now, this isn't exactly that, but it's anyway. If you want to figure out like how fast was she walking, you have to say relative to what? Was she walking some speed relative to the plank or relative to the ice? Right? So when I'm specifying here, he throws the ball at some speed. I'm telling you it's relative to the ice, which is the most straightforward way I could give it to you. Now, you might argue, well, if you started from rest, that would also be throwing speed. And you're right, it would be one and the same in that case. But if you have people like sliding around and throwing things, then you'd want to make a distinction like, if you're sliding while you throw it, then what is the speed the ball is going? Is it your throwing speed or is it relative to the ground? Okay. So anyway, this is the most straightforward way I could give it to you. What is each person's final velocity? Let's say after Chad catches the ball. So here are their masses. Right, so mass of Alan, 40 kilograms, mass of Chad, 45 kilograms. They've got a 1 kilogram ball, which is a pretty heavy ball, about 1 kilogram, like this guy. Right. Alan threw the ball this fast relative to the ground. Right. So after Chad catches the ball, how fast are these guys sliding around? I think you can get that before I finish my attendance. Oh, I've got something in the chat here. Yeah, Zoe? Yeah, come on. Right, so Alicia Petrocelli, absent, but I think we got everybody else. Right, did anybody figure out the answer to this question? What do you think, Kevin?
I think the speed of Alan, MA, will be 0.63 meters per second. And I think that Chad, MC, his final velocity will be 0.54 meters per second.
Yeah, those sound about right. Right. So Alan would be moving backwards at 0.63 meters per second, said, and Chad would be moving forward at 0.54 meters per second. Yeah.
Technically, one would be negative.
Right. Right. Yeah. If you report it as a velocity, right? And let's say right was the forward direction, then you're right. Alan's mass or Alan's velocity would be negative. Right? So how do you solve this? You want to really treat this as two separate problems, right? Alan throwing the ball is one problem by itself, and then Chad catching the ball is a completely separate problem. Right? Now the general idea is sum of momentum initial equals sum of momentum final, something like that. Okay? And of course, this is all in one dimension. We're making some simplifying assumptions, like this is basically horizontal. The ball just moves horizontally. We just care about the horizontal components, things like that. We've got mass of Alan times velocity Alan before he throws the ball, plus mass of the ball times the velocity of the ball before it's thrown, equals mass Alan, velocity Alan after throwing the ball, plus mass ball, velocity ball after throwing, something like that, right? This would be for Alan throwing the ball. Okay? Now it's a really general setup, right? All of the little momentum bits before the collision, I'll say pre-collision, have to equate with all the momentum bits added up post-collision. That's conservation of momentum. Right? Now, hold on a minute. If Alan was just standing there with the ball to start with, then how much momentum was in the system to start with? Zero, yeah. Zero, you could say 0 kilogram meter per second. You could say 0 Newton seconds, right? Equivalent unit. Okay? So there was never any momentum in the system to start with. That means there's never any momentum in the system at all? Yeah, it's technically true because you're going to have a negative momentum plus a positive momentum. It still has a 0 out. Right, so let's go mass Alan, velocity Alan, post-collision. Well, I'm saying collision, but this is really a collision in reverse, isn't it? Like if you filmed this and you ran the camera backwards, you ran the film backwards, it would look like a collision. Okay, so we're treating it like a collision, even though it's like throwing it. Okay. Plus mass ball, velocity ball, final. Okay. I hope we have three of these three things so that we can solve for this. Okay. Do we? Oh, we know the mass of Alan was 40 kilograms. So there's 40 kilograms. Velocity, Alan, final, solve for that. We put, okay, the ball was 1 kilogram. And Alan threw the ball at 25 meters per second. 25 meters per second. Oh, you know what? I mentioned something that was maybe maybe nice like what I meant to say earlier. What is Alan's full throwing speed? Is it a little bit more or a little bit less than 25 meters per second? Like if he was standing on ground and had his feet planted into the ground.
More.
Yeah, slightly more, right? Because you have to consider this plus his speed, right? Maybe you can throw like 25.6 meters per second, something like that, right? But if he's getting kicked back at the same time, that's why the speed relative to the ground would be what it is, right? All right, so 2 algebra steps, because this is all equal to 0. Subtract this term over, give you negative 25. Divide by this coefficient, 40 kilograms. I'm looking at, oh, yep. Velocity, Alan, after throwing the ball, is negative 0.625 meters per second. Right. If I keep 2 sig figs, there's a rule I've read before that general rounding rule. I've seen a rounding rule that you always, if it ends at 5, you round up. I've also seen a rule, I think this more applies to science, that you always round to the nearest even number because then it's a 50-50 shot. So instead of rounding up all the time, sometimes it's not down there. So if I kept 2 sig figs, I might say, if I assumed I had 2 sig figs to work with, I might say something like this. Okay. Okay. All right. Then let's switch over and look at Chad catching the ball. Okay. And could we do something that's very similar to this? So I'm going to say the ball's on the move, Chad's about to catch it, and set up a conservation of momentum for Chad catching the ball. So I got the mass of the ball times velocity of the ball plus the mass of Chad times velocity of Chad. Oh, this would be before he catches it. Right, so remember, it's a completely separate problem from the last one. Okay. And then couldn't I modify the right side of this equation a little bit? Okay. Because when Chad catches the ball, that is perfectly lit. So the final velocity of Chad is really the final velocity of Chad plus the ball together, isn't it? Okay. So I got the mass of the ball plus mass of Chad. And then, well, I'll say velocity of Chad like we're solving for that, but really it's Chad plus the ball moving together, right? That's it. Okay. Oh, now I started off with 2 terms here. It looks like 2 terms. Is one of these guys actually 0?
Yeah.
Which one?
Yeah,
because he starts from rest. So that guy's gone. Okay. So it's just mass of the ball times the velocity of the ball coming in. It's equal to mass ball plus Chad times the final velocity of the 2 head up. Okay. I know the ball was 1 kilogram. It's coming in at 25 meters per second. Let's see, 1 kilogram shows up again. Chad was 45 kilograms. So altogether it's going to be 46, of course, times the final. So really it looks like it's a 25 divided by 46, and then all the units play out. So velocity final for Chad, let's see, I think I switched somewhere. Velocity Chad final, like that, is 0.54 and 347 something meters per second. Yeah. Let's compare these two side by side. It looks like Alan and Chad had pretty similar speeds, obviously opposite directions. Alan was going a little bit faster than Chad, right? Because Alan didn't have as much mass, right? Less inertia, right? Makes sense why that magnitude's bigger. Questions about this so far? Because I can think of some other questions, maybe that that AP might like to ask you. Remember how AP really likes center mass questions? Right? Let's think about what's going on with the center mass within the system. Right? So let's consider maybe a three-object system. Right? So Alan, Chad, and the ball. That could be three objects in the system. Right? And to start off with, where would the center mass? Remember, they all started at rest. Where would the center mass start out? It'd be pretty close to the geometric center, but slightly closer to which guy? Yeah, a little bit closer to Chad because he has a little bit more mass, right? But so maybe about where that X is. Well, I should really put the center mass like up here, right? Pretty close to the geometric center, maybe a little tad bit closer to Chad, because right? We've got 41 kilograms here, Alan plus the ball, 41 versus 45. Right? And would that center mass not be moving? Okay. Then Alan throws the ball. Now, when the ball is in mid-flight, like exactly like the picture shows, Alan's moving backwards, the ball's moving forwards, Chad is still at rest. What is happening to the center mass of that three-object system? Guys, is there an external force on these guys? Not horizontally, which is all we care about. I mean, you could argue that, well, they have a weight and a normal force, but those balance out anyway, right? I could basically treat this three-object system as a closed system, couldn't I? Right? So as long as there's no external force on that three-object system, can the center mass even move? No, it's stuck right here. Right? What about after Chad catches the ball and starts sliding to the right? Does the center mass still stay? Yes, it does. Yeah. The center mass never moves the whole time. In fact, if all you knew was center mass information, you would never know when Alan threw the ball. You would never know when Chad caught the ball. It would just stay right there the whole time. Yeah, yeah, the ball is part of the center mass. Right? So yeah, let's get a little bit more granular, dive into this. So Alan throws the ball to the right, and Alan slowly moves to the left. Right, we got a number for that. It was not quite 1 meter per second. And the ball moves really fast to the right, right? Like that. Right? Now, between them, the center mass between Alan and the ball started right here, didn't it? Started right here. Right? That doesn't move either between Alan and the ball while the ball is moving. So again, we're ignoring the vertical stuff. We're just focused on the horizontal. Okay? So ball moves very fast to the right. Alan moves slowly to the left, but Alan has so much more mass. The center mass between Alan and the ball stays exactly where it started. Okay? Now, that gets thrown out of whack as soon as Chad catches the ball because the ball would slow down a whole lot, wouldn't it? Right? So the ball's velocity almost goes to zero. Not quite zero because Chad and the ball slide off to the right, but very slowly. Right? So, yeah, at that point, you couldn't really make a whole lot of sense of that anymore. Okay? What about Chad catching the ball? Right? So the ball's coming in really fast. See, Chad is just standing here at rest. Now, while the ball is in motion and Chad's about to catch it, is the center mass between specifically the ball and Chad also moving? Yeah, it would be. It would be moving to the right, wouldn't it? Right? Is moving to the right at the exact same rate that it would be after Chad catches the ball and they move together? Yep, sure is. Right? And then if you consider the center mass moving to the right, which would be 46 kilograms at that point, right? Chad plus the ball, moving to the right. And then Alan moving more quickly to the left, and he has a slightly smaller mass, right? 40 versus 46, okay. 45 plus 1. Okay. Then in total for the three objects, yep, that's the center mass of the three objects never moves the entire time. It's always right there. Okay? You guys got that? Because there's no external force on those guys. All right, so let's do here we go. We'll do this later. Don't worry about this quite yet. Okay, so gonna do a really kind of extended demo with you guys. It's sort of a lab, but not have you guys copy anything. Okay. Here's the picture setup. So we'll do this in class. Obviously, you guys get to see this work out too. But I've got some carts on a low friction track. Well, they got wheels, and there's very low friction in the system. Okay? And I've got two basic setups going on. Okay? Now, these carts do have magnets on them, and one setup, the same side magnet is spaced out like north and north. Okay. You guys, north and north, is that attracting or repelling? Repelling, right? Repelling. Okay. And let's say I have one part just sitting there and I ram another one into it. It's going to look a lot like those Newton cradle balls, where they just like boing, just like bounce off each other, and there's a complete transfer of momentum and energy. Okay. This will be what, elastic or inelastic? Elastic, good call. Okay. Versus the other setup, I've got like north versus south. Okay. So those are going to collide and stick together, aren't they? And what that be called? Inelastic. Okay. All right, so we'll get to see each one of those. Also, we can go back and change some things. Like I could throw maybe a weight on this guy, or we could change the weight if we want to, throw more and more weights, something like that. It's like, like as we change these masses of these things, maybe the velocities, like, how do these collisions change what they're doing? Okay. Oh, no, one thing you might be thinking is like, as these magnets are getting close together, I guess either case, right? Wouldn't the magnets have an effect on each other as they're getting pretty close? Like the point of the magnets is to make this like bounce off each other for elastic or stick together for inelastic. But if they're like a centimeter apart, there would be a force on both parts from each other, right? Right. Now that will change the motion of the carts individually, right? Like they'll be speeding up closer together if it's opposite, or start repelling each other as getting close for the north and north. But would this magnetic force between the two carts be external to the two-part system or internal to the two-part system? External or internal, if my system is my two parts? You see it's internal, right? They're just like either pulling or pushing, either pushing or pulling on each other. Right? Yeah, it's just internal to the system. So the net effect, well, there's no external force on these parts. Right? Okay, you could argue weight and normal force, but that balances, and we don't really care about that so much. Okay? So this is basically a closed system. Okay, you guys get it? Yeah, Morgan? Oh, yeah, that's true too. So then as you increase the weight, would you be increasing the friction? Yeah, so for the inelastic especially, this is not the prettiest of you. You'll see that the friction does kind of matter with this one, and you'll see when I switch the camera over. Okay. For the elastic, we're trying to get a negligible friction, and elastic actually works out pretty well. It's actually pretty close to no friction. So yeah, the friction would go up a little bit. This is a good thing to consider too. Yeah. But, okay. Now, if we did do this lab, then what would the data table look like? And I want to walk you guys through that so you can make sense of this, because this could be an AP style question, or there could be an AP style question related to something like this. I mean, this is just classic collision spot, right? So I did post this on Google Classroom. There are two tables that look very similar to each other, but they're slightly different. So one says perfectly inelastic. One says general, but it's really good for the elastic one especially. So let's start with the inelastic one because it's a bit more straightforward. This is where the two parts collide and stick, right? And there are two halves to this table. There's pre-collision and post-collision, right? So before the collision, after collision, right? And then what have we got down here? Something about total momentum before collision, total momentum after collision. This looks like maybe an experimental way to see if conservation of momentum is actually true, right? Maybe something like that. That's kind of the, looks like where you'd be going with a data table like this, right? So let's dig into the table, see what the columns are. See what would I measure, what would I calculate to get to that point. Right, so first couple of columns are measure the mass of each cart in grams, right? Mass of cart A, mass of cart B. Okay, makes sense. Now, normally we work with kilograms in this class, so if you switch units, then just keep a note of that. Right? Same thing with distances. We normally use meters, so if you're measuring centimeters, just keep track of the two. Right? Now, this is saying how far does something go in centimeters, and how much time does it take to do that, so that you really care about this column, a calculation column that says velocity, the velocity of cart A pre-collision. Right? How would you find the velocity of the cart pre-collision? Well, you could have a motion detector, or you could have this here meter stick and this here stopwatch. So let's see if you guys are following. When I say X, does this X refer to, in the context of this table, is this X referring to a position or a displacement? Okay, displacement. All right, you guys all got that. Nice. Because how far did it roll and how much time? yeah, be careful about the context of that. Right. The other cart, well, I started its initial velocity at 0. I just said from rest. Okay, so we have a sort of a simplified example here. Right? Then what is the total momentum in the system pre-collision? Well, all the momentum comes from the cart that's in motion, because the one at rest has 0 velocity, 0 momentum, right? So it'd just be mass A times velocity A, right? So, oh, great. So you can know the quantity of momentum before the collision. You guys got that? Right? I bet if I asked you guys to make the second half of the table from scratch, you could probably figure it out. Right? For perfectly inelastic, so this would be the one where they stick together, and start with this one because it's a little bit more straightforward. Right? Then wouldn't the object after the collision be like one giant, like sum of the masses, right? Moving at some common final velocity? And what would that velocity be? Well, here's where you have to break up the meter stick and the stopwatch again. How far did it roll and how much time? So you can figure that out. Right? And then you could multiply this together, get the total momentum in the system after the collision, and then you could compare numbers. So supposedly, I mean, if conservation of momentum clearly applies, then this pair of numbers should be pretty close, this should be pretty close, and so on all the way down. Isn't that true? Okay. Now, that's all assuming that there's no friction in the system, and you'll see how this is technically rigged up. For this particular setup, the inelastic ones, didn't quite get rid of friction as well as I might like to. So, all right, I'm going to show you guys something really tricky. You guys ready for something tricky? If you don't follow this, don't worry about it. If you do, then it's, I guess, one extra skill that you could have. Right? So I've had students actually perform this in the past. Right? And like I said, this is a really tricky one to measure it. How far does it go and how much time and blah, 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 right? You could do it, it's just kind of tricky. But because the cart actually does roll to a stop, that means there's friction going on, right? So if you do total distance over total time, let's say the car actually does come to a stop, and the distance you measure is the total distance the car went before it came to a stop, right? And that's what I've seen students do in the past. Let me make a velocity versus time graph. Velocity versus time. Okay? Now, assuming that the cart would be slowing down uniformly, let's say here's the collision at time 0. So bam, and then the rest of this graph is going to be post-collision. You guys get that? Okay. When the cart slowed down to 0 velocity, right? Something like that. Okay. And guys, if you do total distance over total time, what velocity are you actually calculating? Initial, final, or average? Average, right? Isn't total distance over total time the average velocity? Right? So V bar equals total stopping distance over the time to stop. Right? And where's V bar on this graph? Would it be, yeah, like exactly halfway up. So if you actually wanted the true post-collision velocity, the post-collision, then how would you get that from average velocity? You would double it. You guys see that? Assuming uniform acceleration, or slowdown rate in this case. Yeah, you would double it. So this should be approximately 2 times V bar. And in fact, since I've had students do this in the past, that's like a really common thing to do. They'll end up finding average velocity, not realizing the difference. And then their momentum site consistently end up being like 50% of what it should be. So this actually does work just with this trick kept in mind. Okay. Right. But that's deeper than I want to go with you guys, but that's maybe something to think about. Okay. Right. Let's switch over and look at the elastic case. Okay. So that was inelastic. Right. What about elastic? Right, now, this one's a bit trickier because since they bounce off each other, you have to think, well, after the bounce, you have to keep track of 2 carts because they each could do something a little bit different. But the first half of the table is exactly the same. Okay? I want the mass of each cart. I'm going to let one cart just start from rest just to simplify it a bit. What's the speed of the cart in motion? Well, you have to know how far it rolls and how much time, and then divide those 2 things. Okay? So you measure, calculate. All right, and so where is it here? Right. Okay, then you can calculate the momentum in the system before by doing mass of the cart times how fast it's going. Like that. Okay, get that number. Exact same as before. Okay, now here's where this is different from before. Is post-collision. So post-collision, each cart is going to move a different distance in some time. Okay, so some distance to cart A, some distance to cart B, the time it takes to get there. Really, maybe I should have made 2 separate time columns in case you wanted to really look at each cart independently, but I'm sitting here, maybe just one person with one stopwatch. Okay. So what is this? What is the velocity of each cart after collision? And then if you want to know the momentum of the system, well, you have to get it for each cart. So momentum of cart A, momentum of cart B, add them together to get the total momentum. And if everything is really conserved, then this pair number should be the same or very close, this pair, and so on all the way down. You guys see the logic of that? Okay. All right, so yeah, it's good to just know how that works. But like I said, we're not actually going to do this. Right, so I put these tables away. Okay. And let's break out, where is it? This one. Okay. And so everybody at home has this page out. This is a new page. It's I think it says General Lab Write-Up or AP Lab Write-Up, something like that. If you're looking for it on Google Classroom. Right. Let me pass this out to everybody in class real fast. Oh, okay. Okay. All right, so everybody got one? Yeah, thank you. All right, so we're going to do 2 labs class today. Okay. Let me show you guys the general setup for these things. So here. All right. So one is going to involve bouncy balls. So we're going to have these 3 balls. We're going to bounce these off the floor, and then I'm going to record what was the drop height versus what was the rebound height, right? And we'll do a data table for each of those situations. Okay. Now, what's the question here? What are we trying to figure out? I will leave that up to you. I can think of several good questions for the bouncy ball situation. Okay. Now, of course, it has something to do with momentum and impulse. There's a collision of the ball against the ground. Right? Done some problems that look kind of similar to this back on Monday. Okay? After we do this one, we'll do a separate lab for measuring. Oh, sorry, I shouldn't tell you guys. I should have you guys come up with questions. Now, here's what the setup looks like, though. Right? I'll take this pen, I'll unscrew it. Right? I'll take this cartridge, push it against the spring. Right? Here's the spring. Okay? Here's the cartridge right here. Push it. Okay. And then let it fly. Now, I originally wanted to aim this vertically, but the cartridge kept slamming against the ceiling tiles. So yeah, so we'll turn this into a projectile. Right? So if I know the height that I shoot it from and how far it goes, and I know maybe the mass of the cartridge, and I know how much the spring is being compressed, then maybe there's something you could figure out from that. I could think of one particularly good question. Now, if you guys do want to do this right, I'll give you guys a choice. You can either do bouncy balls as a write-up or spring cartridge, the ink cartridge as a write-up. Okay, so just pick one. If you do the ink cartridge one though, then think more along the lines of last week's stuff. This is better as a conservation of energy lab. Okay, so something to do with that. But if you choose bouncy balls, then that's totally this week's stuff. Okay, something to do with momentum, impulse, something like that. Right, guys good? All right, now when you guys are I'll have you guys record the data for both of these though. Okay, now 2 ways to record the data. One way is that you could just take this page, flip it over to the blank side, and divide the paper in half and do them side by side. If you do that, exactly like you guys are seeing on the screen, you do have to write kind of small, so you may not want to do that. I'm going to right now copy the left half over on a bigger piece of paper. Okay? So I'm copying this while you guys are copying this, the one on the left side. Okay? So we're copying this one right now, so the left side of this paper. So bouncy balls. And then, while you guys are finishing that up, that too, another thing I want to mention is for this data table, remember how a really good science practice is to do like several measurements for each trial? So let's try that. I'll do 3 different drop heights, and then we'll do like 3 trials for each. Okay? So like take an average or something like that. All right. Okay, let me switch my camera over. Oh, I never did collisions with the guy. I'm sorry. Right, here. Well, I need to switch my camera over anyway. Okay. To set up this collisions. Sorry, I almost forgot to do this one. So we're going to do some carts colliding first, and then we'll do the tennis balls. Sure. Right. Where's start with? Start with the golf ball. Okay. All right. So let's look at inelastic. Something that would be inelastic. Okay. Now, like I said, these won't roll quite as well, so I had to break these up like this. This was the best I could get a low friction system, something like that. Okay. So, okay, yeah. So not perfect, but maybe not terrible. But yeah, it does like to stop. Okay. Now, one thing I'd want to know is what is the mass of each one of these parts? So let's use this classic triple balance beam. So it's zeroed out right now. Okay. So zeroed out. Okay. What's the mass of this guy? Not too much. All right, so looking at looks like 509.5 grams, like 509 grams. Okay, so just a little bit more than half a kilogram. Take a measure. The other one probably pretty close to that. So something like that. Okay, so we got the mass. Okay, let's see what happens when when these magnets are oriented so that they'll stick together. Okay. What's going to happen if I slam these guys against each other? Ooh, okay, something like this. Okay. So I do see after collision, they stick together and, well, the one in motion definitely slows down, and the one that was stopped gets going. Okay. What if I change masses by throwing like 1 kilogram here? So this is 1 kilogram plus the 509 grams. So I almost tripled the mass of this guy. Ooh, how's that going to affect things? This one a little better? I think so. Let's try this way. They can imagine if you were actually doing this collision lab, you want to say, well, you know, how far has it gone in centimeters? How much time has passed? If you're watching this on video, you might be able to do that, right? Maybe take advantage of the video and pause it and slow it down. Okay. What if I put the big mouse on this guy, have the little guy run into it? Ooh, like almost a dead stop. Ooh, okay. Yeah, so there definitely is enough friction in the system that it definitely affects the system. Okay. All right, so that's inelastic. What about elastic? Okay, now I'm going to break out these guys. Oh, let's grab the mass of at least one of them. Probably all pretty close to each other. Ooh, oh, look at that. Look how well this guy rolls. Maybe I should have just gone with all those. Yeah. Take some magnets onto that. I'll probably do that next year. All right, just use those cards. Roll so much better. All right, let's see. Mass of this guy, probably pretty close to 500 grams. Oh, wow. Almost exactly. Yep, that is exactly 500 grams. Pretty much on the nose. All right, 500 grams. So, okay, so 500 grams, just slam these guys against each other. Ooh, look at that. That looks like Newton's cradle, doesn't it? Where one ball transfers all its momentum and energy to the other one. So yeah, that's just about perfectly elastic right there. Probably closest you'll ever see. What do you think happens if I throw, say, triple the mass of this guy? No, this guy is 1 kilogram plus half a kilogram. This guy is 3 times as massive as this guy now, right? What do you think's gonna happen? Ooh, so this guy slammed into you, starts moving really fast. This guy keeps moving forward, but not as fast. See a couple more times. Whoa, man, this guy really takes off, doesn't he? Just eyeballing it, looks like this guy moves faster than this guy was originally moving. Kind of crazy. But I bet you could do a momentum conservation. Yeah, it sure does, doesn't it? I bet you could do a momentum conservation and that works out in the text. Right? What if you take the light guy and push against the heavy guy? Wow. Okay. I think I was getting used to bounce off each other earlier, like rebound. Not really seeing a lot of rebound. What if I do, this guy is now 7 times the mass of this guy, 7 times the mass. Uh-oh. Yeah, now we're getting this rebound effect. Okay, for boing, bounces off. Okay, about this way. Whoa, yeah, look at that. Okay. Now we got 7 times the mass. This one's like, get out of the way. Ooh, yeah, this guy really takes off. Whoa. Yeah, it's like, I don't care, get on my way. All right, enough collisions. Pretty fine. That was a poor choice of orientation of the wheels. All right, you guys ready to bounce some balls? Do it. All right. Yeah, it's the way to go out in the lab, right? Like Mythbusters. Like, we're done here, blow it up. All right. So, dropping this golf ball. Let's have the original. Oh, I didn't get the mass of the golf ball. We gotta get the mass of the golf ball, right? Now, depending on what question you ask, you may or may not need to know the mass of the golf ball. I can think of some questions where you would need to know it. I can think of some questions where you would not need to know it. So let's go ahead and get it as a data value anyway. Okay. How much is a golf ball? What's the mass of a golf ball? I'm sure this is a Googleable number, but do it the science way. Probably 2 grams, right? I wonder if it's more than 10. Oh, wow. A pretty hefty little golf ball. 40 something. Ooh, getting close here. Almost balanced. I think right about there. Let's call it 46 grams. So the mass of the golf ball is 46 grams. You guys got that? 46 grams. Okay. Bounce this against the floor. I'm just going to drop it and see where it bounces up to. All right, so starting from, let's get some drop heights preloaded. Let's switch my camera real fast. So I might see. Oh, that's an idea. Yeah, Morgan's asking, should you want the mass in kilograms? Yeah, you could. So either put the mass in kilograms, or if you recorded it in grams, I was saying like 46 grams, right? Then if you're doing some calculations later, just remember you probably want to convert that to kilograms. That's a good idea. Right? Let's do 100 centimeters. This will be in centimeters. The rebound height I'll also measure in centimeters. Again, if you're doing calculations with these things, then you may want to convert to meters later. Could be a good idea. Then we'll do 80 and 60. See what happens from that. Or change my mind. Let's make this last one 40. Just something like kind of smaller. Kind of all the room I have on that page then. Okay. And let's do the same thing with the other balls. We'll measure everything in centimeters on this page, centimeters all the way down. and we'll do 180, 40. All right, so starting with this 46-gram golf ball. There. So from 100 centimeters, let me try it again. Ooh, went up to 76. 77. 77. Okay, you guys got that? 76, 77, 77. Okay. Now let's take this down to 80 centimeters. 80. Up to 60. 64. And 62. Now let's jump way down here to 40.
What were the ones for the 20?
What were those three values? Okay. Yeah. Okay. And then from the 40 centimeter mark, let's try that again. Put that one. I was getting 31. 31 again. And 30. Okay. You guys with those? Okay, so you guys got 9 total rebound heights for the golf ball, right? Okay. Okay, let's switch over to the racquetball. All right, racquetball time. Get the mass of this guy. What's the mass of a racquetball? Oh, looks like it's really close to the mass of a golf ball. Try and hold it in place here. Need more level surface. Balls rolling. There's no flat side of the ball. So it's really close to this. Yeah. You know what I could do? What if I threw this tape on here and I zeroed it out from there? Ah, now I'm thinking. Okay. So the tape itself is 61.5. Okay. So the tape itself is 61.5. And the tape and ball together is 103.5. What's the difference between those two? 42? Right, then, oh, yeah, okay, that was pretty much what I was getting anyway for the ball by itself. So 42 grams for the mass of the racquetball. All right. Oh, bounce time. So from 100 centimeters. You always do the first one as a trial run. That's about where it's going to go. Ooh, this guy's really bouncy. Let's call it guys 78. 80. And 79. Now, from the 80 centimeter mark, got 63, 65, and 67. Ooh. And then from 40 centimeters, getting 34, 34 again, and 34 three times in a row. So 34 centimeters 3 times in a row. Guys good so far? Okay, you guys online doing all right? Looks like don't see anything in the chat. I think we're good. Okay, and then finally, the tennis ball. Okay, let's grab the mass of the tennis ball. That's showing up in the, yes. Got rid of that light. Hold on, what am I doing? Oh. Hmm. 56. 56 grams. Guys got 56 grams? 56 grams on the tennis ball. From 100 centimeters up. I'll try it again. 59. Oh, 59 again. And 61. From 80 centimeters, we got 53, 50, and 53. Then from 40 centimeters, got 28. Oh, whoops, messed that one up. 29 and 29. Okay, you guys got this? Okay, in here. 49, yeah. So at this point, you should have all the data for each of those, all the data on this page should be filled out. Okay? Guys good? Any questions on that one? All right, so let's switch over to the other setup. Okay. Now, again, there are many questions you could ask about that data could help you answer. So if you want to do right up to that, then figure out what you could answer from that data. Okay? Or maybe like this other one more. So I'll have everybody record the data for this at least, and then you, like I said, I'll have you guys pick which of these you want to do the actual write-up for. But everybody go ahead and record the data. So I'm going to record, I'm going to redraw this table on a big piece of paper while you guys are doing the same thing. Okay. Cartridge. You guys got that? Right. So remember, if you do the e-cartridge write-up, think more along the lines of conservation of energy than what we're doing this week. So it's more of a last week kind of lab. Right. We need to grab the mass of the cartridge. It's going to be important. I want you to know, how much is the spring being compressed? So if I push this cartridge into this spring, how much is it compressed? Okay. And then we're going to make projectiles out of this, where we're just going to fire it horizontal and see how far does it land on the floor. Ooh, this looks a lot like that coffee cup problem, doesn't it? Okay. And I'm going to measure height in centimeters and distance in also centimeters. Let's do a similar idea with the test balls. We'll choose 3 different starting values, and we'll do 3 trials for each set. Okay. So let's fire it from, let's do the same values. Why not? 100 centimeters, 80 centimeters, and 60 centimeters. Or sorry, we did 40 for the balls. 180 and 40. And then we'll do 3 trials on each one. This ruler. Right. Trial 1, trial 2, trial 3. Trial 1, trial 2, trial 3. Trial 1, trial 2, trial 3. Okay. Yep. Turn the sideways so it fits in the screen. Pull this balance over here, triple beam balance, so I can get what is the mass of this cartridge? So what I'm doing, okay, so I think everybody in class and on camera can see this pen right here, right? If I unscrew this ballpoint pen, okay, then it's like different parts, right? So there's this cartridge. This is actually going to be the projectile, right? This cartridge, right? Now I'm going to push it into this spring right here, the spring. Okay. All right, now how much does it get compressed, and how much is the mass of the cartridge? I want to know both those things. Well, since I got the triple balance beam right here, let's get the mass of the cartridge. So make sure it's all zeroed out. Okay. Yeah, it's zeroed out. Now, how do I know it's zeroed out? Because if it's zeroed out, see this right here? This mark is going to line up with this 0. So if it's really heavy, it's going to go point like that. If I've got these pulled over too much, it's going to fall down like this. And right when it's balanced, it'll just kind of float right next to 0. And that's how I can know that it's measuring the correct mass. So put this cartridge right here. Okay. Probably a couple of grams, right? Let's see. Looking at, oh, wow, I said a couple of grams. It's 2.0 grams. It's exactly a couple of grams. Wow. So 2.0 grams. There you go. Mass of this cartridge. Exactly 2 grams. Used a different cartridge last class that I think had more ink in it. But it's a factor. Okay. All right, so great. We got this number. Exactly 2 grams, 2.0 grams. Okay. Next number down, how much is the spring actually being compressed? Because it's being compressed like some consistent number, right? If I just press it in all the way. Right? I'm thinking probably order of magnitude of about 1 centimeter, right? You know, how much is this here spring right here get squashed? Okay. Let's find out. I gotta figure this out. See, one way I could do it is to put this next to your ruler, of course. Right? If I look at the end of this cartridge and I line that up with the 0, however much it gets smashed, that would be the amount of compression. So let's see what that would be. I'm looking at, let's see, from there to there, line this up. Okay, so it's like right now there's 0 force on the spring, but not for long. Okay. now I'm putting a force, I have to put more and more force to squash it more and more. 1.3 centimeters, 1.3. Okay, so this number is 1.3 centimeters. Okay. Guys good there? Who needs me to say any of these numbers again? You guys have all these numbers? Okay. All right, now it's projectile time. So we're going to let it fly from each of these heights. We'll do 3 trials for each one, okay, and see where does this thing land. Okay. So let's turn this camera. Oh, got something in the chat here. What was the spring number? 1.3 centimeters. Then the mass was exactly 2.0 grams. So, gotcha. So we'll start from 100 centimeters up. That'd be the full length of a meter stick. Oh, unwind this thing. And, oh, well, if I want to know how far it goes, I better lay down some meter sticks. Okay, so just gonna shoot straight up this aisle. All right. My launcher, my projectile. All right, here we go. All right, so from 100 centimeters up, aim it straight horizontal for as best as I can. All right, I'll look at it, it's probably right about here. All right, let's call that 253. Thank you. Everybody got 253? The first number? Put this down, 253. All right. Let's do it again. Yeah. So take 2, also from 100 centimeters. Horizontal. Looking like right here. Looks like 234, I think? 234? Oh, okay. 234. Pretty close. Trial 3. Oh, that one went a long way. Would that be 244-ish? 244. Alright, let's lower the height a bit. Now, if I lower the height, is it going to go further or less far? Yeah, definitely less far. Right. Less far how much? Well, the time it was in the air, it's a function of the distance, but there's some kind of square root relationship going on there, so it's probably not going to be linear, but true, it wouldn't go as far. Right. All right, so take 1 at 80 centimeters. Oh, that went a long way. So never mind about not as far. I went 235, I think. 235. 235. Now, take 2 from 80 centimeters. Oh man, that one went a long way too. I'm looking at 230. 230. And take 3 from 80 centimeters. Oh man, it's really flying. Like 240. 240. It looks like the average of those is less than the average of from 100, but not a whole lot less. Right? Right, but let's cut that distance in half, or the height in half, I should say, to 40 centimeters. So now we're going way close to the ground. So only 40 centimeters above the ground. In a level, and look like it landed right here. That would be 154. We got 154. Take 2 from 40 centimeters. Oh. 145. At 145. Okay. And last data point of today. Last data point of lab day. 40. Oh, that went 161. 161. What's that? So, guys at home need to grab that data, then, most of it anyway. Once you just click it. Okay, did anybody miss any of those? Or got any questions so far? All right, and time we're going to class. We've got a good 20 minutes in here. All right, so this is what we do is, like I said, you have a choice of which of the last 2 labs you want to do a write-up on, and also what question you want to ask. What question you ask is up to you. Like I said, for the bounce balls, I can think of several good questions. For the ink cartridge, I can actually think of at least a couple of good questions for the ink cartridge, depending on which way you go on that. So, yeah, so pick one of these, pick a question, right? And then on this page, write your question, and then follow the format. And by the time you get to your conclusion should answer your question based on the data that we gathered for one of these labs, whichever lab you pick. That's good. Yeah, Morgan?
If there was like if there was no friction and you included the displacement after it hits the ground, would it always slide to the same spot regardless of how high it was?
You said there was no friction?
Mm-hmm.
If there's no friction, it would just, like, they would still be sliding, right? They would just keep going on forever.
Oh.
Right? Yeah, right? Yeah. And then, if there is friction, then let's say if it's going twice as fast, it should go 4 times as far. Right? Yeah, that whole thing, right? Right. So, how's it worked out last class is that students needed most of the rest of the class to finish this lab. If you do pop in the rate tray, then you don't have to worry about it for homework. If most of you guys are finished within the last 5 minutes, then we'll do some conceptual questions related to momentum. Okay? But I'll give you guys some time right now. Okay. Actually, I'll go ahead and just stop recording now since you guys have some class time to work on this lab.